Hello everyone, welcome to GATE classes. This is lecture 2 on operating system, and in this lecture we are going to start a new topic, that is protection. Protection. So the very basic or very simple questions which will come to our mind is question number 1 is why we need protection. Why we need protection? That is the first question which will come to our mind. Second question is from whom we need protection. And third question is to whom. So from whom we need protection and to whom we are providing protection. And last question is who will provide protection. Who will provide protection? Are you getting it? So these are the four basic questions which will come to our mind. First question is, after all, why we need protection. Second is from whom we need protection, and we want to provide protection to whom, and who will provide the protection. These are the four questions which will come to our mind. So why we need protection? This question I will ask. I will answer in few slides. From whom? So we need protection from user program. Okay. So here user program is just like a, you can say, enemy or something like that. So so we need protection from user program. And to whom? To whom? Hardware. Okay. So we want to provide protection to hardware. We want to provide protection to hardware from user program. And who will provide that protection? So who is the hero? Enemy is user program. Who is the hero? Hero is obviously we are studying operating system. So operating system is the hero here. So who will provide protection? So OS will provide protection. So finally, I can say OS will provide protection to hardware from the user program. Okay, now I will answer this question. Why, after all, why we need protection? Okay. So first of all, please tell me what are the hardware resources in computer system, which we have actually studied in the previous class also. In the lecture 1, we have discussed about it. So we have three things in hardware. Okay, broadly we can have three things. The very first is I/O devices. Second is memory, or you can say main memory, and the third one is CPU. So please try to remember this thing. Secondary memory. Secondary memory is a type of I/O device only. So do not get confused, sir, where you have written secondary memory and so on. Secondary memory is a part of I/O devices only. Okay, hard disk, CD-ROM, all these are I/O devices, input-output devices. Okay, and main memory is the second important hardware, and third is CPU. Okay. Yeah. So yes. So and one more question that will come to your mind is, sir, why you are calling secondary memory as a I/O device? See, we can take input from it also, like you want to read a file from hard disk. That is, so it's acting like an input device, and you want to store something in hard disk also, like you want to write something or you want to write a new file in hard disk and so on. So that can act as output device also. Okay. So hard disk can act as well as input device as well as output device. It can act both ways. Okay. So that's why we are calling secondary memory as I/O device. Okay. So I/O device, main memory, and CPU. These are the three things in the hardware. Okay, now I will ask the question, or I will answer the question of why, after all, why we need protection. So first of all, let me tell you about I/O device, input output device. See, we can imagine that we have a multi-user operating system. Multi-user means multiple users log in and do their task, like in Unix operating system. Okay. So we can imagine, or let me do it on the next slide. Let me jump to the next slide. Yes. So now I'm going to answer, after all, why we need I/O protection. Why we need I/O protection? So answer is very simple. We have to just see, we can have multi-user operating system. For example, we have multi-user operating system. For example, Unix. So multiple users are login and they are doing their work. Now chances are there one user can access file of another user. That means unauthorized access can be done. Imagine a scenario where teacher and students who all are communicating with the same computer, or you can say a mainframe computer. Okay, let me give you a small idea about Unix. Okay, so we have a mainframe computer, and from that computer we have multiple terminals or dumb terminals are attached to it. Why we are calling them as dumb terminals? Because they are just keyboard and monitor. They do not have any processing capability. So all the processing is done here. That is the mainframe computer or centralized system. And these are the terminals. Okay, on this terminal, user will sit and do their task, do their work. Here, user will sit and do their work like this. So you can imagine multi-user operating system. Okay. Now chances are there that this person try to access a file which is owned by this person. For example, he is a teacher. Okay. So he is a teacher who is teaching you some subject, and he is a student. Now, obviously, what student wants? Student want to access the question paper which teacher has designed. So obviously, if every student will come and see the question paper and so on, so obviously there will be no question of exam and so on. So we want to protect the files. The basic scenario is we want to protect the files. So all the files are in hard disk. Okay, all the files are in hard disk. Now, so whatever user, see, if student want to access this hard disk, so student cannot access this hard disk directly. Rather, student will request the operating system, and operating system on behalf of user will access this hard disk. Are you getting it? So user or student will first request the operating system, and then this operating system on behalf of this user will access the hard disk. So why on behalf of this user student OS is accessing hard disk? See, if you student directly access the hard disk, then he can access, or he or she can access anything. So that may create problem. So first of all, student will request operating system, and operating system will first check whether he is authorized to do that or not. So so operating system may give you some pop-up window, and OS may ask you the username and password and so on. So if username and password is given correctly, then you are authorized, or you can say then you are allowed to access the file. Otherwise, you are not allowed to access the file and so on. I hope I have made the point clear to everybody. Okay, so that's why we need IO protection. So student should not access hard disk directly. Even teacher should not access hard disk directly. They will first request the OS, and then OS on behalf of these users will access hard disk and give information to them. Are you getting it? So that is the basic meaning of IO protection. Okay, yeah. So that's why. So to prevent, so in one word, I can say to prevent unauthorized access, we OS will do these tasks for you. Okay, so you are not allowed to access IO devices directly. Are you getting it? Even you can think of keyboard, monitor, and so on from that also. Okay, so for example, see, actually, IO device must be locked first. It must be locked, and then it can be accessed. So now chances are there, user apply lock on say keyboard, and he is never releasing it. So he is never releasing the lock. So other cannot access that. So just a sake of example, I'm telling that's it. Okay, so this is an example of why we need IO protection. Yeah, so next was main memory protection. See, why we need main memory protection? That is again similar kind of scenario. Main memory protection. See, each and every process, okay, each and every, see, what user is doing? User is writing programs. So user is writing a program called user program, okay, to do any kind of task and so on. So now when this program start getting executed, this program will become process. So program under execution is a process. Roughly, you can say it like that. But in the next lecture, most probably, I will tell you the clear-cut definition of what exactly process is and so on. Actually, program under execution is not a process. Process is having lots and lots of extra things. So we will come to that after a few lectures. Don't worry about that. So roughly, for presently, you can say for today's session, roughly you can imagine program under execution is a process. Okay. So now each process, I am assuming that it is stored in main memory in contiguous fashion. For example, it has started from location 2000 and it is going till 3999. Okay. So this is the, you can say, program which is stored in main memory, and now it is a process. Now each and every process has a process address space. Each and every process has a process address space. What is process address space? Process address space is the area of the main memory in which the process is stored, or area of main memory to which process has access. Okay, so process cannot access entire main memory, because if process is allowed to access entire main memory, then user will write a program in such a way that he can access some sensitive areas of main memory, like that of operating system, and he may you can say he may edit a part of operating system in RAM and so on. So your computer may crash and so on. So something disaster may happen. So to avoid all these things, each and every process has a process address space, and each and every process should remain in its process address space. It cannot go outside it. That means it cannot access memory which is outside its process address space. It's very simple scenario. See, this is your you can say your city in which you are living. Okay, so now this is your home. So this is the land to which you can access. You cannot access land which you do not own. That is the scenario here. Okay, so process cannot access the memory which it does not own. So it can access only that memory which it owns. Okay, so the memory which it owns is known as process address space. Now I think you have got the clarity. Okay, so if you keep on going, if you keep on accessing others' land, then obviously it will create problem for you as well and for others as well. Okay, so better is you should remain in your house only. You should access the land of your house. You cannot access entire city land and so on. Yeah, that is the scenarios here also. Okay, so process should remain in its process address space only. It cannot go outside, or it cannot access memory which it does not own. So, but if you can say user program or process wants to access memory which it does not own, then immediately trap should be generated. Immediately trap should be generated. Trap means what? I think you already know about it. We have studied in the previous class also. Trap means what? Trap is an event generated by CPU to stop the program under execution. So immediately program under execution will be stopped. Okay, because the process is doing some illegal activity. The illegal activity is what? He is trying to access the memory which it does not own. That's it. So I hope I have made the point clear. So that's why we need memory protection also. Okay. So if process try to access main memory which it does not own, then obviously it may hamper the code of other process, or it may hamper the code of even operating system. So your computer may crash or something bad can happen. Okay. So that's why we need main memory protection. Last is CPU protection. Okay. The last is CPU protection. So why we need CPU protection? That is again very simple idea. See, for example, user process is executed on CPU only. So user process, or you can say program which user has written, is like this: while one, and there is some body of the loop. So while one means what? Infinite loop. So it will keep on executing. So it will never leave the CPU. So chances are there, once you start a user program, it will never leave the CPU. Hence, we need CPU protection also. So how it is done, don't worry about it. We will show you all these things in subsequent slides. The only thing is I have just given you the answer of why. Now please jump to the previous slide. Now I think you have got each and everything perfectly. See, first of all, who will provide protection? Operating system. To from whom? User program to hardware. So OS is providing protection to hardware from the user program. User program is just like, you can say, enemy type. Okay, so user program can access hardware and it may not leave it and so on. So this is your hardware and this is your user program, and user program does not directly access the hardware, because if it directly access the hardware, then chances are there it may do some malicious activity and so on. So better is OS is present between user program and hardware. So user program will give instruction to operating system, and accordingly OS will first check whether uh, the operation which user program wants is correct or not, or is it authorized to do that or not. Once authorization or something all is done, then OS will do the task of the user program. So OS will do the same task on behalf of user program. Okay, so now OS will access the hardware and take the data and so on, and then it will give to user program and so on. Okay, so OS is just like acting like a middleman. So OS is protecting the hardware from the user program. And why we need protection, I have given you the idea. That means why we need IO protection, why we need main memory protection, why we need CPU protection. And so now I think the picture is absolutely crystal clear to everyone. Okay, now let me start in detail. First is IO protection. So let me start what exactly is IO protection. What is IO protection? Okay. So for IO protection, we have dual mode of operation of CPU. Dual mode of operation of CPU. So what is dual mode? Dual means two. So CPU will work in two modes. Okay. CPU will work in two modes. The very first mode is known as user mode. Very first mode is known as user mode, and second is known as kernel mode. Second is known as kernel mode. Kernel mode, or you can say privileged mode, or you can say supervisory mode, one and the same thing only. Okay, supervisory mode, or you can say monitor mode. All are one and the same thing. Okay, kernel mode, privilege mode, supervisory mode, monitor mode. These are the four names for this. Okay, second mode, and first mode is user mode. Okay, so first is user mode, second is kernel mode. So another name of kernel mode is privilege mode, supervisory mode, monitor mode, and so on. Okay, so these are the two modes in which CPU will work. So see, as the name suggests, user mode means what? User program will start running in user mode only. User program start in user mode. User program start in user mode of CPU. CPU will start executing what? See, what is the aim of CPU? CPU is just CPU will keep on executing the instructions only. So the main task of CPU is to execute the instruction. How instruction is executed? You have studied in your computer architecture subject: instruction fetch, instruction decode, and then execute, and so CPU will just keep on executing the instructions. So, and initially it will be in the user mode. So user program, whenever user writes a program, so obviously finally what we are writing in a program, we are writing some instructions. So those instructions will be fetch, then decode, then execute, and so on. If I assume that program is written in high level language, then obviously first compiler will come, and then it will convert it into assembly language, and that assembly language code will be executed, and so on. You already know all these things. I am not going into all such details. That will unnecessarily waste our time and so on. So the main thing is, we can imagine user program has been written by user, and one by one its instructions are executed on CPU. So initially, mode of the CPU will be user mode. So user program start in user mode. Okay. Now user program, see, actually, okay, let me give you a small idea. Then I will come back to here. Do you know what is ISA? Instruction set architecture. ISA. ISA is instruction set architecture. Instruction set architecture. You have studied that in your computer architecture subject. If you have not studied, don't worry. I will just give you a small hint. ISA is instruction set architecture. So in ISA, we have two types of instruction. What exactly is ISA? ISA is set of all possible instructions which are supported by your CPU. Set of all possible instructions supported by CPU. Set of all possible instructions supported by CPU. So all the instructions which are supported by CPU, that is ISA. Set of all those instructions, like your CPU support add instruction. Okay, add. It also supports sub means subtraction, multiplication, division, jump if carry, jump if not carry, dot. There are lots and lots of instructions. Okay, you have studied them in our computer architecture subject. So if you make set of all those instructions, that will become ISA, or instruction set architecture. Now ISA is divided into two parts, or you can say we have two kinds of instruction in ISA. What are these two kinds of instruction? One is known as privileged instruction. One is known as privileged instruction, and second is known as non-privileged instructions. Non-privileged instructions. Okay, non-privileged instructions. Okay, privileged instructions and non-privileged instructions. So privilege means what? They are given some special importance. That's why these are privileged. We say na he is a privileged baby. Privileged baby means his father and his parents are very rich. He is born in a very rich family and so on. Privilege means he has something special, or these are some special things which have been given some special status. So these are privilege instructions. Okay. So example of privilege instructions are which deals with IO. So all the instructions which deals with IO, these are known as privilege instructions. For example, read, write, and so on. Okay. Read is an instruction which is used to read something from hard disk. Write is an instruction which is used to write something in hard disk, and so on. So these are some examples of privilege instructions. So simply you can say privilege instructions are those instructions which deals with IO. That's it. Okay. So instructions which deals with IO, that is known as privilege instructions. I'm not writing all these things. Please, you can make your notes yourself and so on. Okay. Otherwise, it will waste our time. That's it. Non-privileged instructions which do not deals with IO. Which do not deals with IO. For example, you write add, sub, mul, div, and so on. All these are simply non-privileged instructions. Okay. So now coming to the modes, user mode. In user mode can execute only non-privileged instructions. Okay. Non-privileged instructions. This can be executed in user mode. And privileged instructions are executed in kernel mode. Okay. And in fact, kernel mode can execute non-privileged instructions also. Kernel mode can execute non-privileged instructions also. So for non-privileged instruction, it hardly matters to me. Mode can be the user mode, kernel mode, it hardly matters to me. But for privileged instruction, mode must be kernel mode. Okay, so now see the previous slide now. So I have told you user program start in user mode of CPU. So that means user program will start running it initially in user mode only, because initially we may have some instructions which do not deal with IO. That's why I'm saying that user program will start running in user mode only. Okay. So now you may say, sir, what exactly do you mean by user mode or kernel mode? So let me tell you a small idea. I'm jumping to next slide. Please pause the video and note it down. Yes. So user mode, as the name suggests, user mode means in which a user program has complete control over CPU. User program has complete control over CPU. That is known as user mode. What is kernel mode? As the name suggests, kernel mode means what? Kernel has complete control over CPU. Kernel means a part of operating system. I will tell you, don't worry. Kernel is exactly heart of operating system. Let me tell you here, no problem. Kernel is what? Kernel is heart of operating system. Okay, we have already studied what are the, you can say, uses or application of operating system in the previous class, where I was telling you that memory management, process management. When I was discussing the syllabus of OS, I have told you memory management, process management, IO management, and so on. So these are the basic tasks or basic applications of operating system. What exactly operating system is doing? So it is doing memory management, CPU management, okay, IO management, and so on. So all these things are done by kernel only. Okay. So heart of operating system, which is doing your you can say memory management, process management, and so on. Okay. All the tasks are done by kernel only. Okay. Yes. So in kernel mode, as the name suggests, kernel has complete control over CPU. Kernel has complete control over CPU. User program do not have control. Kernel has control over CPU. So now I think you have got it, that what these modes are exactly doing. So what I have said, privilege instruction which mainly deals with IO, and I have told you that user program should not directly interact with IO devices, otherwise it may create problem for us. So the idea here will be what? Whenever privilege instruction is executed, mode must be kernel. When non-privileged instruction is executed, no problem at all. Mode can be the user mode or kernel mode. It hardly matters to me. But the key idea or the crux is that uh, uh, the privileged instructions should not be executed in user mode. That is all about IO protection. Because if privileged instructions are executed in user mode, that means what? User program has complete control over CPU. So now user can do anything with IO devices. It may apply lock on IO devices and it may not release it, or it can access unauthorized. You can say it can access files which it does not own, and so on. So student can easily access the question paper which is designed by professor, and so on. So that will create a very huge mess in our computer system. So the key idea of IO protection is what? Privileged instructions should never be executed in user. The key idea is, so what exactly is IO protection? In one line, if you want me to define IO protection, in one line I will say privileged instructions should never be executed in user mode. Should never be executed in user mode. Okay. So if by chance privileged instruction is going to be executed and mode is not switched from user to kernel, that means mode is still user mode, then immediately trap must be generated by CPU to stop the program under execution, because it may lead to some mess, like the student can access a question paper designed by professor and so on. So that will create a very big mess for us. So to prevent this messy kind of thing, immediately trap will be generated by CPU to stop the program under execution. So what I will say, if privileged instructions are executed in user mode, I am writing in shortcut way. Okay, if privileged, PI means privileged instructions are executed in user mode, trap must be generated by CPU. Trap must be generated by CPU. Okay, trap means it will immediately stop the program under execution. Okay, so that is the basic idea of IO protection. Now immediately question will come to our mind, sir, how exactly this mode switching is done and how all these things are done? Let me show you the things. Let me jump to the next slide. Okay, so the idea is that, see, user program is having, I am assuming initially non-privileged instructions. Okay, user program is having some non-privileged instructions. As soon as privileged instruction will come, so all these instructions will be executed in what? User mode. Now, as soon as this instruction will come, this is a privileged instruction. I am assuming this is a privileged instruction. As soon as this instruction will come, mode must be switched to kernel mode. And in the kernel mode, this instruction must be executed. And if by chance mode is not switched from user to kernel, then obviously trap will be generated and our entire program will be stopped. Okay. So now you may argue with me, sir, see, this instruction has not even fetched it till now. After fetching, after decoding, then obviously CPU will come to know, okay, this is a privileged instruction and so on. So mode must be kernel mode and so on. So obviously there are very, very high chances that mode will not be switched from user to kernel and trap will be generated and so on. See, actually, the things do not work like this. See, I have said instruction set architecture, na? Privilege, non-privilege, user. So these are what? These are in assembly language only. I have written add, sub, mul, dev, read, write, jump if, carry, and so on. I think you already know all these are assembly language instructions. So these are nothing but assembly language instructions only. But user has written the program in high level language. Okay, so actually see what user program do not contain these privilege instructions in them. Please try to note it down carefully. User program, user has written code, that's it. Yeah, code, that code does not contain privilege instructions. Okay, user program does not contain privilege instructions. User program does not, PI, I'm writing shortly, PI. User program does not contain privilege instruction. So what exactly user program do? What exactly user program contains? See, user program is written in high level language. So actually user program do a system call. User program will do a system call, and this system call is actually definition of the system call contain the privilege instructions. Okay, definition of the system call contain the privilege instructions. Okay, And let me do it more precisely. Actually, user program don't even contain system calls also. User program actually do normal function calls or library calls. Okay, like you do printf, scanf, and so on. You have studied in C language. We write printf, scanf, and so on. We write like this, na? Printf means what? You want to print something on screen or monitor. So monitor should be accessed. So printf is a library call. Now this printf internally will do a system call. Okay, and that system call definition will contain the code, or you can say that will contain a contain some privilege instructions which will help in printing something on monitor and so on. Okay, are you getting it? So accessing monitor, or you want to print something on monitor, so obviously privilege instructions must be used because we want to deal with IO. Monitor is an output device. So we want to print something on monitor. That means we want to access IO. And IO device, I have already told you. See, whenever we want to access IO devices, we need privilege instructions for them. So the code which actually prints something on monitor, that code will be written in assembly language, and that is part of kernel. And that code will contain what? That code will contain privilege instructions. Are you getting it? Okay. So printf we do library call. In program we do library call. Now this printf will actually call print, or you can say a system call. It will do a system call, and that system call will contain privilege instructions. Okay, and that system call code. See, system call is nothing but a function call only. You can roughly think of system call as a function call, but this function call definition is part of kernel. Okay, kernel is what? I think you have got it by now. Kernel is what? Heart of operating system. That means it contains code for memory management, code for process management, and so on. It is a huge collection of code. That is the heart of operating system. So now if you want to access code of operating system, to access that code, we have to do system calls. Okay? System calls are nothing but function call. See, we do some function in programming language, we make some function. So we do some function call, and definition of that function call is nothing but the code. Okay, code of that function. So like we want to add two numbers, so we will call a function add like this. Okay, and now this add function, whenever add function is called, so control will be transferred to definition of the add, in which we have written the code to add two numbers and so on. So that is the scenario here, same scenario. That means we have just done a function call. So system call is just like a function call, but its definition, or you can say what exactly the system call will do, that is the definition. Huh? So its definition is part of kernel. So here add functions definition is part of user program only because we have written all these things. So system call is a function call whose definition is part of kernel. So roughly we can say system call is a way to interact with kernel. Kernel is what? Let me jump to the next slide. See, kernel is what? Kernel is huge collection of code. Okay, these are codes written, huge collection of code. So now you want to access this code. How you will access? Like you want to create a process. So for this, you will user program will do fork system call. So as soon as fork system call is done, so this fork system call means what? Function is called. So its definition is part of kernel, and here its definition will be executed and so on. You want to create a file in hard disk, so you will do some system call, and that system call will finally call the code of the kernel, which will help in creating the file. That means allocate space in hard disk and so on. Everything will be done. So now I think I have made the point clear to everybody. So this is what kernel, and this is what a system call. So system call is a way to interact with kernel. If you want to execute code of kernel, then system call is one of the way. Kernel is a huge collection of code. So how you will access that code? So if you want to access that code, you have to do a system call. I think I have made the point clear. So system call is an interface between user program and kernel. Simplest way I can say, system call is an interface between user program and kernel. Okay, so this is the kernel, this is user program. So user program want to execute some code of kernel. So user program will do a system call for it. So it is an interface between user program and kernel. I hope I have made the point clear to everybody. Okay. So finally, where were we? So we were discussing that user program actually do not contain privilege instruction. User program will do a library call. Now that library call will actually do a system call, and system call definition will contain the privilege instructions. So obviously in user mode, program will be running. Now whenever library call is done and library call has done a system call, as soon as system call is done, the mode is switched from user mode to kernel mode. So now CPU is in kernel mode, and since it is in kernel mode, then the definition of system call will be executed, which contain both privileged as well as non-privileged instructions. And I have already told you in kernel mode, both type of instruction can be executed. That means privileged as well as non-privileged. So now our tension is over. So directly, indirectly, what we are saying is, so user program will start running in user mode. As soon as user program do a library call like printf, scanf, and from scanf, what scanf is doing? Scanf wants you to type something from keyboard. That means it want to access you want to access keyboard, or more precisely, user program want to access the keyboard. So keyboard is an input device. Okay, so obviously the instruction, or you can say we need some privileged instructions which will try to access your keyboard. Okay, so immediately scanf will do a system call, and that system call maybe say read system call. So that what will do? So definition of that system call will contain privilege instructions. Okay, so system call is a function call. Function call definition is a piece of code, and this code is nothing but part of kernel. I think I have repeated many times, so you have got the idea by now. Okay, so finally, whenever system call is done, immediately mode will be switched from user to kernel, and hence now CPU is in kernel mode, so these can be executed. These instructions can be executed. Now after system call is over, the mode will be switched again from kernel to user. Okay, so now your normal functionality of program will be, you can say your instructions in the program will be executed and so on. Okay, so program will be like this. Now there are some non-privileged instructions, or simple instructions are written, and then we will do a library call, which finally do a system call, and system call definition will be containing some privileged instructions. So for that, mode has been switched from user to kernel, and then when we will come back, okay, and we will resume our program execution. So at that place, mode will be again switched to user mode. Okay, so now I will dig a little bit more deeper, and now I will tell you how exactly this mode switching is done. So see, actually each and every CPU, okay, please pause the video, note it down. I'm jumping to next slide. Okay, yes. So now each and every CPU is having a mod bit. This is a CPU. So with each CPU we have a mod bit, mod bit. Okay, so if mod bit is 0, it means it is in kernel mode. CPU is in kernel mode. And if this mod bit is 1, that means it is in user mode, or CPU is in user mode. Okay, so this mod bit will give you idea about which mode presently we are in, which mode, or presently CPU is in which mode, kernel mode or user mode. Kernel mode 0, user mode means 1. I think I have made the point clear to everybody. Okay, so now how mode switching will be done? Now you have got the idea. So you just have to complement this bit. So if mode switching means what? We are in user mode. Presently we are in user mode, and then we want to jump to kernel mode. Then we will complement this bit. And when we are in kernel mode, we want to come to user mode. Then we will complement the bit, and so on. So you just have to complement this mode bit. Mode switching will be done. So mode switching is done with the help of mod switching is done by complementing the mode bit. By complementing the mode bit. Okay. Now question arises, who will complement this bit? Okay, which instruction will complement this bit? That instruction is known as trap instruction. So please try to follow it. Trap is different thing. Trap instruction is different thing. Trap instruction is used to complement the bit, complement the mod bit. That means it will switch the mode from kernel to user, user to kernel. I'm using the word complement the bit. Now complement means what? 0 to 1, 1 to 0. both will be done. So kernel to user, user to kernel. Mode switching will be done by trap instruction. So what it will do? Complement the bit, complement the mod bit. Okay, so user to kernel and kernel to user, both are done by one instruction, that is known as trap instruction. And trap is completely different thing. Trap, I have already told you, event generated by CPU to gain attention, event generated by CPU to stop program under execution. That was trap. Trap was different thing. Trap instruction is a different thing. Okay, I hope I have made the point clear to everyone. Okay, so this is the story of dual mode of operation of CPU. Okay, so dual mode of operation means CPU will work in two modes: user mode, kernel mode. Okay, in user mode, user program start execution in user mode only, where it will execute non-privileged instructions. As soon as privileged instruction will come, mode must be switched from user to kernel. Because if privileged instruction is executed in user mode means what? User has complete control over CPU. So obviously it will try to do some illegal activity and so on. So before execution of privileged instruction, a mode must be switched from user to kernel. So in kernel mode means what? Kernel has complete control over CPU. So on behalf of user, kernel will do the operation which user program wants to do. So first kernel will check whether the operation is valid or not. If it is valid, then it will be done. Otherwise, it will give us error message and so on. Whatever may be done, that may be a separate part. If it is an implementation part, I'm not going into that much detail. Okay, so the basic idea is mode must be switched from user to kernel. Now question arises, how this mode switching will be done, and how before execution of, see, that is a very important point, how before execution of a privileged instruction mode is switched. We have not executed this instruction. CPU has not even seen this instruction. Before seeing it, how CPU is predicting the future, how CPU will say this next instruction will be privileged and so on. Actually, CPU is not predicting the future. CPU is not doing anything. What we are doing is user program does not contain privileged instructions directly. If user program contains privileged instructions directly, then obviously it will be very, very difficult for us, because CPU cannot predict the future. It has to first fetch the instruction, decode the instruction, and then it will come to know, okay, it is a privileged instruction and so on. Okay, so anyhow, it is not done like that. So user program will do library call. Library call will do a system call, and then system call definition will contain the privileged instructions as well as some non-privileged instructions. So in user mode, as soon as library call is done, it will do a system call, and before executing the definition of system call, okay, or before executing the code of kernel, okay, because definition of system call is what? Part of kernel. So before execution of that, mode is switched from user to kernel. Okay, now in kernel mode, these instructions will be executed, or definition of system call will be executed. Okay, line by line we want to execute it now, because we want to read something from hard disk and so on. So it will be a small program in assembly language which will do the task and so on. So how to read the data from hard disk, how data will come in RAM and so on. Each and everything, for each and everything we have written a code. Okay, there is nothing called automatic in operating system. For each and everything we have written a small code. So it is so it appears to us that everything is done automatically, but nothing is done automatically. For each and everything, we have written a small code. I hope I have made the point clear to everyone. Okay. So finally, yeah. So finally, from user mode to kernel mode will be switched by your trap instruction, and then this code will be executed. So a system call code will be executed, and then after that, mode will be again switched from kernel to user, so that normal program execution will be resumed, and so on. That's it. So this is all about your IO protection. Okay, so the in one line, if you want to define what is your you can say this IO protection. So privileged instruction should never be executed in user mode. That is the one line for IO protection. You can define like this. Okay. Yeah. And what is a system call? System call is nothing but an interface between user program and kernel. So whenever we want to execute code of kernel, or whenever user program want to execute or want to access code of kernel, then it must do a system call. Okay? Yeah, I hope I have made the point clear. Because see, this is very simple now. See, we have a code. Now how you will execute this code? Obviously, you have to do a function call now. Then control will come here, and then this code will be executed. Without doing function call, how this code will be executed? That is not possible. We have to do a function call, and that function call is system call. Okay, yeah, that's it. So this is the basic idea of your system calls. Okay. Yes. So see, and so for what kind of task we have system call? Let me give you a small idea, because we are talking about system call. Let me give you a small idea. I'm jumping to next slide and I will show you something about system calls. I'm jumping. Please pause the video, note it down. Yes. So now let me give you a small idea about system calls. So the very first and the very basic point is system call is an interface between user program and kernel. It is an interface between user program and kernel. UP means user program. Okay. And it is the only way with the help of which user can execute code of kernel. You have to remember this thing. So the only way user program can access or execute code of kernel is system call. Okay. The only way with the help of which user program can execute kernel code is with the is by system. The only way with the help of which user program can execute kernel code is by system. Without system call, user program cannot execute kernel code. Okay. So for what kind of task we have system call? Okay. Next question is, for what kind of task we have system call? So see, whatever task which you do not know how these are performed, for those tasks system call is present. Like we do not know how exactly process is created. So for that we have a system call. System call for process creation. For system call. We do not know how process is killed. Okay, how process is killed. So for that we have you can say exit system call. Okay, and so on. So for each and every task for which we do not know how these tasks are done, for that we have a system call. Like we have we do not know how actually we read some data from hard disk. How exactly we read some data from hard disk. So for hard disk we have system calls like read system call. We do not know how data is exactly written into the hard disk. For that we have write system call. Okay, and so on. So for whatever task which we do not know how exactly it is performed, for those tasks we have system calls. Okay, I hope I have made the point clear to everyone. Okay, so for kernel, I have already told you, kernel is a huge collection of code. For kernel, I have already told you, it is a huge collection of code, which is used to do process management, memory management, etc. All the task of your operating system is done with the help of kernel. Okay, yeah, let me jump to the next slide. So kernel is huge collection of code. So this question has been asked in GATE many times, so please listen this carefully. This is a kernel, so it has a huge collection of code. Okay, this is some code is written and so on. Yeah, this is a huge collection of code. That is a kernel. So when you want to execute a code, or how many entry points are there to the kernel? Entry points means what? How you can access the code of kernel. So the first way, which I have already told you, is a system call. User program will do a system call and then code of kernel will be executed. Any other way? Yes, interrupt. Whenever interrupt will come, we have to execute interrupt service routine. Na? So interrupt service routine, ISR, I have told you in the previous class. ISR is obviously part of kernel only. Okay, so how interrupt is handled and so on. So that is part of kernel. So this is the second entry point to kernel. Third entry point is trap. Whenever trap is done by CPU, we want to kill the program under execution. So how killing will be done? So for that we have code in operating in kernel. So trap is the third entry point. And last is signal. We have done in previous class one. So interrupt, trap, signal, and system call. These are the 4 entry points to kernel. Entry points mean these are the only 4 ways with the help of which code of kernel can be executed. For user program, there is only one way, that is system call. Obviously, user program cannot do interrupt, trap, or signal. Okay, it cannot be done. Interrupt is generated by an IO device to gain attention of CPU. I have told you that in previous class. Trap is generated by CPU to stop program under execution. Signal is given by user for the program under execution and so on. Okay, so if user program wants to you can say run code of kernel, so the only way is by system call. Yes, so these are the 4 entry points to kernel. 4 entry points to kernel. These are the 4 entry points to kernel. And user program, how user program can interact with kernel? There is only and only one way, that is system call. I hope I have made the point clear to everyone. So let me draw a small picture for you, okay, so that you get more clarity. I'm jumping to next slide. So it is said now, picture is worth 1,000 words. So it's better to make a picture than speaking 1,000 words and so on. So firstly, we have hardware. So hardware, on hardware, okay, or you can say hardware, to interact with hardware, we have a huge collection of code that is known as kernel. So kernel can interact with hardware directly. Now to interact with kernel, we have system calls. Okay, and who can do system call? Obviously, user can do system call, user or user program. So how it is done? With the help of C. Actually, see, this is a user. Okay, now user can interact with operating system with the help of C. If you have a mouse and so on, so that is graphical user interface. Okay, or if you are working in DOS and something, so we have character user interface, like user type in commands and so on. So you type command to create a file, you type command for each and everything. Now we have, like Unix, we have PS command, okay, to know the process status and so on. So what are the process currently running in OS? That is, for that we type PS command, LS command, list command, LS list. LS means list. So you want to list the files in the current working directory and so on. For that we have ls command and so on. There are lots and lots of command in Unix. If you have studied, then it's okay. Otherwise, no need to do all these things. It is not in your competitive exams and so on. Particularly in GATE, it is not present. So we can just leave it. I have just given you a small idea. So that is PS, LS, and so on. We type some commands. Now that is character user interface. So that means user is interacting with OS by some typing characters and so on. And if you have mouse and so on, then we are doing graphical user interface. So we have either GUI or CUI. So user will interact with GUI or CUI. Okay, and then all these things will indirectly communicate, do system calls. Like you double click on an icon, so obviously new process will be created now. So how these are created and so on, that is done by system call. So system call will actually, it is an entry point to kernel. So system call is just a function call whose definition is part of kernel. So now kernel code will be executed and so on, and kernel code will directly interact with hardware. Okay, so for example, we want some memory for a file. So for file, we want some memory. So how this memory will be allocated? So obviously this memory will be allocated in hard disk and so on. So that is done with the help of kernel. So that is the basic scenario. So hardware, so that kernel can directly interact with hardware. System call is an entry point to kernel. GUI and CUI, these are character user interface or graphical user interface. So these are the interface with the help of which user interact with OS. I hope I have made the point clear. Okay. So system call is also known as API. API. You have something, you have heard about it. API is application program interface. Application program interface. That is system call. Okay. So I hope I have made the point clear. So from this diagram, questions can be asked like everything between system call and hardware is what? Kernel. Okay. Everything between kernel and GUI CUI is what? System call, and so on. Okay. So this question has been asked in many competitive exams. Everything between system call and hardware is what? Everything between API, application program interface, and hardware is what? Kernel. I hope I have made the point clear to everyone. Okay. Yes. So now let me jump to the next slide. So now this is all about your dual mode of operation of CPU. That is IO protection we have done. So with IO protection, I have told you few more things. That is what is kernel, what is system call, and so on. You have got the idea by now. Okay. And there are 4 entry points to kernel. This question has been asked in many competitive exams. What are the 4 entry points? Trap, signal interrupt, system call. Okay. Yeah, that's it. So now we will do main memory protection. IO protection is over. Now we will do main memory protection. So I have already told you why we need main memory protection and so on, because each and every process has process address space, and no process should access others process address space. No process should access others process address space. Are you getting it? So say in main memory we have P1 process. Here we have P2 process. So P1 should not access memory of P2. P2 should not access memory of P1 and so on. So we need memory protection. So how it is done? So I am discussing very traditional or very old techniques. So we have two special registers. We have two special registers. Okay. So the very first is base register, and second is limit register. Okay. So what is base register? Base register store, as the name says, it is the base. Base means what? Starting location of process address space. A starting location of process address space. Starting location of process address space is stored in base register. What limit register store? Limit register store size of process. Please try to remember it. It will store size of process. That is limit register. Okay. So CPU will generate address. Okay. CPU will generate address. So that address, it will be first, you can say, compared with base value. So that value, the address generated by CPU, that should be greater than or equal to base value. Na? For example, see, let me give you a small idea. Let us suppose this is the process address space of any process, and it is starting from through 2000, and size of process is again 2000. Okay, so it is starting from 2000, or let me say it like this, you may get confused. So process is starting from memory location 1000. Okay, and size of process is 2000. So size of process is 2000 and contiguous memory is allocated. So till which location it will go? So you may think, sir, 1000 is the starting location and 2000 is the size. So it will go till 3000. No, it will go till 2999. It will go till 2999. Why it will go till 2999? Because 1000 location is already in use now. Okay, are you getting it? So from 1000 to 2999, how many bytes of memory are there? So like in array, we have studied upper bound minus lower bound plus 1. So 2999 minus 1000 plus 1, it will be 2000 bytes only. So 2000 bytes process. See, on 1000 location, 1 byte of process will be stored. Na? We cannot left 1000 as blank. Na? So obviously from 1000 till 2999 we will go. I hope I have made the point clear. Yes. So obviously CPU generated address is say 1500. So 1500 will be first compared with base value, that is 1000. So whatever address is generated by CPU, that should be greater than or equal to 1000. Na? That is done here. So it should be greater than or equal to base value. Okay. Now, if yes, then we will go further. If no, that means it is not less than or equal to base value. That means it is strictly, sorry, it should be greater than or equal to base value. So if this statement is false, that means what? CPU generated address is strictly less than base value. That means it is somewhere here from 0 to 999. From 0 to 999. If this address is generated by CPU, obviously we will generate a trap, because process cannot access the memory which it does not own. We have told you in the few slides back also. Okay. So immediately trap will be generated. No means trap. Okay. Now if by chance yes come, that means memory is address generated by CPU is more than 1000. So it may be more than 2999 also. It can go to 3000, 4000, 5000 also. So you have to keep track of upper limit also. So for that, I have already told you we have a limit register. So limit register stores size of process. So what I will say, I will add these values, base plus limit. I will add these two values, base plus limit, and this and address generated by CPU, that should be strictly less than this. Why? Base value will be what? 1000. Limit value is what? Size of process, that is 2000. Are you getting it? Base value is 1000. It is starting from 1000 location. Limit value means what? Size of process, that is 2000. So 2000 plus 1000, 3000, na? But we want till 2999. So I have used strictly less than here. So CPU generated address should be strictly less than base plus limit value. If yes, then we will go to main memory and access that location. If no, then trap will be generated to stop the program under execution. So this is how main memory protection is done. Okay. I hope I have made the point clear. Please pause the video, note it down. I will jump to the next slide. Yes. So the last is CPU protection. Last is CPU protection. Yes. So how CPU protection is done? I have already told you, chances are there that user program will never leave the CPU. So we want that user program will always leave the CPU. Directly we want this thing. So once user program has control over CPU, so we have to make sure that it will always leave the CPU. It should not happen that it will never leave the CPU. Like we have while one loop and so on. We have discussed now. We have a while one loop like this. So obviously program will be keep on executing. Okay, it will never leave the CPU. So to prevent that, we have two separate hardwares. Okay, we have two separate hardware. So the very first is system clock, and the second is timer register. System clock, second is timer register. System clock, see, each and every CPU is attached with a clock. You have already studied in your computer architecture subject. Each and every CPU is attached with a fixed interval clock called system clock. Each and every CPU is attached with a CPU is attached with fixed interval clock. Fixed interval clock called system clock. Okay, so you have heard about that like we have 1 gigahertz CPU, 2 gigahertz CPU, 3 gigahertz CPU. You have already heard all these terms. So these terms are related to system clock only. For example, if I say I have a clock of 1 gigahertz frequency, 1 gigahertz is what? 10 power 9. So what directly indirectly what does this mean? Each clock tick is 1 upon 10 power 9. That is nothing but 1 nanosecond. So with 1 nanosecond, we have a clock tick. So in each clock tick, something is done. Like with one tick, instruction will be fetched. So in 1 nanosecond, instruction will be fetched. In next clock tick, instruction will be decoded. So in 1 nanosecond, it will be decoded. Now in next clock tick, it will be instruction will be executed. So next 1 nanosecond, instruction will be executed. So directly, I will say each instruction will be executed in 3 nanoseconds. Are you getting it? So system clock means what? 1 gigahertz system clock means what? 1 nanosecond is clock tick. And in each clock tick, something will be happen. Like we have 1 megahertz processor. If we have 1 megahertz processor, megahertz is what? 10 power 6. So I will say in each microsecond, okay, 1 megahertz means what? 10 power 6. So each tick will be in 1 upon 10 power 6. That is 1 microsecond. So in each microsecond, uh, instruction will be fetched, decoded, executed, and so on. So so here roughly I will say 3 microsecond are needed to execute instruction. Here I will say 3 nanosecond are needed to execute instruction. So obviously 1 gigahertz processor is much better than 1 megahertz processor, and in fact 1 gigahertz processor is 1000 times more faster than 1 megahertz processor, because here in 1 microsecond task will be done, here in 1 nanosecond task will be done, and so on. So I hope I have made the point clear what exactly system called clock. And anyway, you have done all these things in your computer architecture also. 1 megahertz clock means 1 microsecond. Something will be done, or 1 tick in 1 microsecond, or here 1 tick in 1 nanosecond. Okay, so that is system clock. Okay. Next is timer register. So timer register, so as some random value will be stored here in timer register, not exactly random. Let us suppose 50 is stored here. So in timer register, we have stored a value 50. So with each clock tick, this value will be decremented. So when this value will be 0, CPU will be snatched from the process, or CPU will be preempted. Preempted means it will be snatched from the user program. Okay, so obviously no user program will be allowed to control CPU for arbitrary amount of time. Are you getting it? So now user program cannot hold the CPU for infinite amount of time, because user program can do like this: while one ends on, it will keep on executing. So obviously CPU. So you may think that CPU is slow, but actually CPU is doing some other task in the background. Okay, so to prevent all these things, we have two separate hardware: system clock and timer. So timer register is 50, which means what? 50 for 50 clock ticks. A user program, or you can say program, is allowed to use CPU. After 50 clock tick, it will become 0, and as soon as timer register will become 0, CPU will be snatched from the process. So obviously load timer register. So load timer will be a privileged instruction. It is not a general instruction. Okay, because if it was a general instruction, or it was non-privileged instruction, then user can give a very large value here, and that may create problem for us. So load timer is a privileged instruction. Load timer is a privileged instruction. It is not so privilege means what? In kernel mode it will be executed, and so on. I hope I have made the point clear to everyone. So timer register. So unit of this 50 is what? 50 second, 50 millisecond, 50 microsecond, 50 nanosecond. What is this? So unit to this timer register is given by system clock. So if we have 1 gigahertz system clock, then it means 50 nanosecond. If we have 1 megahertz system clock, here 50 means 50 microsecond, and so on. Okay, so these two separate hardware are used to provide CPU protection. I think now everything is crystal clear to everyone. Okay. Yes. Okay, so that's it. So this is all about your protection. So we will stop here. In the next class, we will do types of operating system. Okay. Yeah. Okay. Thank you so much. Bye-bye.